This is joint work with Reid Barton, who's in Steve's group at CMU. And I want to talk about condensed type theory. So at some point I'll give a very brief idea of what a condensed set is, but you don't really, one of the points of condensed type theory is you don't really need to know what a condensed set is, because you can just fool around with condensed type theory and get a bit of a feel for them. So there are some motivations or historical reasons for why we worked on this project. And here's one, which is maybe some sort of aspiration or dream, that is having a computer algebra system for general topology. So there's a lot of software out there to work with like topology over the real numbers, numerical analysis, etc. And if you squint a bit, then you can use cubical AGDA or something like that as a computer algebra system to work with homotopy types. But what if you want to say, like, let X be a topological space, and you want it to be a sort of random topological space that doesn't necessarily behave like the real numbers and also has actual points instead of a homotopy type that all the points are sort of quotiented out by path equivalence. And so our project provides a first step towards something that could eventually maybe become a computer algebra system for general topology. But like at the moment we're very far from the computability aspect, so you can't really compute. But anyways, then another motivation is coming from maybe directed type theory, something like that. So what's the point of directed type theory? Well, in mathematics, to give a functor, you give the action on objects, and every sol can infer the action on morphisms, so you just never do that. But computers don't have a sol. So directed type theory wants to make a theory where you just specify what the functor does, where every object is some sort of category, and where every function is automatically functorial with the correct variance. So some functions will be covariant, some functions will be contravariant. And so condensed type theory provides some results of this flavor, which was quite surprising when we stumbled upon it. And I want to state this result at some point in the talk. That's sort of my main goal for today. And then, so some historical background, like why did Reid and I start thinking about this? So at some point, I think 2 years ago, Reid joined the math department in Freiburg for a year as postdoc, and we were working together. So the background story is Clausen and Schulze did this liquid analytic ring structure on the real numbers, and that proof doesn't really fit in a human brain, according to Schulze. So then we verified the proof in the liquid tensor experiment, and that project was just finished when Reid showed up in Freiburg. And so we were thinking a lot about what is actually going on in that proof? Can we reorganize it? Can we use tools from logic to restructure the proof in such a way that maybe it does fit in a human brain? And we did lots of things, and at some point condensed type theory rolled out of that, where we stumbled upon these weird things like directed univalence, but we didn't really actually manage to simplify the proof. So the Clausen-Schulze proof still doesn't fit in a human brain. C'est la vie. But that's sort of maybe not a motivation. It certainly is like a historical explanation for why we started doing this. And hopefully, eventually, maybe it will become a motivation that we can actually reorganize the LTE proof. Okay, and then a few weeks ago, I learned that there's another group in Sweden around Thierry Coquin, Cherubini, Galix, who are also working on something they call condensed type theory. And so we met with them and we exchanged some ideas. And so they have a different starting point and a different axiomatic setup. There is some overlap, there's also some difference, and certainly our motivations and applications are quite different. So I think it's really nice. It's sort of, there's enough to talk about, and there's also enough that we can sort of still publish our respective papers that we have in mind, so that's good. Yeah, but yeah, it's certainly worth looking into their project as well if you're sort of interested in what's going on. So the starting point is that we'll be doing type theory. So we take Martin-Löf-dependent type theory, and then we're going to do a bunch of stuff on top of that. And so the first thing that we do on top of that is that we postulate two predicates of type.
What do you mean by the identity types? Which identity types?
So I'll do like classical type theory, but I'll talk a little bit about univalent, like hot later on. There are some issues there. So I sort of want to do both. So I'm just going to punt on the question for now. Anyway, so we have two predicates. One is called CHaus, and the other is called ODisc. If you want, you can read etal instead of ODisc. And we abuse notation and consider these predicates also as subuniverses. So we'll say that X has type CHaus when we mean X is a type and it satisfies the CHaus property. And informally speaking, so how do we think of these predicates? Well, every type we think of as a topological space, or if we want to be a bit more precise, as a condensed set, but like it's going to be a gadget with some topological source on it. And if A has type CHaus, it means that we think of A as a compact Hausdorff space. And if A has type ODisc, we think of A as sort of a classical discrete thing. So the O in ODisc stands for overt, which is something you never learn about in topology because every topological space is overt. But it turns out that in synthetic topology, there is this notion of overtness, and it's important, but for this talk, you can just ignore it. So when you see ODisc, just think discrete, and then at some point, if you want to understand the details of the talk, you get confused, and then you need the O. But yeah, just ignore it. I kept it in because it means that ODisc also has 5 letters, just like CHaus. So for symmetry, you need it. Okay, and so if we want to be slightly more precise, you want to do something with a context. So if you have a type A that is CHaus in context gamma, then you semantically interpret that as that the map A to gamma is a proper map. So, like in the sense of topology, right? Mapping compact stuff to compact stuff. And
Putting compact stuff to compact stuff.
Right. Yeah, sorry. The image of compact is yeah, inverse image of compact is compact. But no. Yeah. That's what a proper map is. And then if A is ODisc, then the structure map A to gamma is a local homomorphism. Right, so it's cool that we have these two predicates, but of course just having two predicates doesn't give you anything. They need to interact somehow, so we need a bunch of axioms on top of that. But this is sort of the data part, and now we explain a whole bunch of property part of the axioms. So these two subuniverses, CHaus and ODisc, they're closed under a whole bunch of constructions. So finite products, finite disjoint unions, quotients, formation of equalizers, like if the kernel pair is in, if you have an object in CHaus or and you have some equalizer, like both objects are in CHaus and the kernel pair is in the quotient. No, wait, equation nonsense.
Right.
Like,
Equational stuff, right?
Right. Sorry.
Fine. So.
I want to say equalizers, and I was talking about co-equalizers.
Yes.
Anyway, if everything is living in a certain subuniverse, then these limits and colimits will also live in the same subuniverse.
So is
Of course,
it
I
all
support
colimits? Or is that all colimits?
finite.
Oh, equalizer means what? Equalizer of two morphisms?
Yeah.
Oh, okay.
And then finally, formation of sigma types. So that's somehow an important one. Which means that if you have an indexing type A, that is CHaus, and you have a family of CHaus types indexed by A, then you can form the sigma type, and that sigma type will also be in CHaus. And if you replace, if you put ODisc everywhere instead of CHaus, then the same axiom, or that analogous axiom is also true. Or true, like false, we postulated. And then, like, we can't go classical because problems, but we still want some version of the axiom of choice. And so there is this thing known as collection. So that's what we can postulate. And it looks like this. So you have a morphism f, or a function, I guess, between two types. And the type at the bottom, y, is assumed to be CHaus. And the map is supposed to be surjective. And now the ordinary axiom of choice would say, okay, then you can find this map splits, there will be a section. But we can't do that. So what can we do? We can say, well, then there exists a different type y prime that is also CHaus with a surjective map G to y. So it's a cover. Which you can think of this as sort of like you replace y by a cover, so now you're looking locally on y. And then there will be like a local section S that splits F. So you could call this like a local axiom of choice for CHaus types. And note that X can be anything. X doesn't have to be CHaus. And then we have the same thing for the subuniverse ODisc. Okay, so that's sort of, and this turns out to be in practice really useful. Like this axiom is used a lot as a replacement for the axiom of choice. Yeah?
In the classical case, if things are indeed topological spaces and compact Hausdorff topological spaces, is that true with continuous map? In classical mathematics, the axiom of choice give you right inverse, but they never give you continuous right inverse for anything.
No, but I think this should work because you can replace your base y by something. So I mean it's true in condensed sets, so it must be. Like maybe you have some pathological topological spaces that you can use for X, but like because the transition from topological spaces to condensed sets is not completely possible.
If X is locally compact, then you might be able to make y prime a subset of X.
Yeah.
Sort of taking.
Okay, I can't think
Subset of X.
right now, but I'm happy to think about this later. Whether it's true in topology, but it's true in condensed sets. Okay, so now we saw that the universe, like the subuniverse CHaus and ODisc, they're both closed under formation of sigma types, but we haven't talked about pi types yet. And so now we'll talk about pi types, and that basically boils down to postulating Tichonov's theorem. So if you have an indexing type that is just like a classical discrete set, and you have a family of Hausdorff spaces, so CHaus types, indexed by I, then you take their product, and that's going to be CHaus. So this is just, like classically, this is just Tichonov's theorem in topology. Product of compact spaces is compact. And dually, if you have an indexing type that is CHaus, so this is something that you don't really know from topology maybe, and you have a family of discrete spaces indexed by I, then the product will be discrete. And so a special case of this is the compact open topology, where you're looking at functions from a compact Hausdorff space to a discrete space.
So just to be clear, if I was the constant function, is a point ODisc? Like
Yes.
Unit ODisc?
Yes.
So X can send every element of I to unit.
Sorry, every?
Ah, I see. Okay, huge product of units is still discrete.
Yeah.
Okay. Well, I believe you.
Okay, then, so whenever you have a function from a compact space to a discrete space, the image is finite. And so that's somehow a fundamental fact of life. So we turn it into an axiom. We have a compact Hausdorff space X and a discrete space Y, and every function from X to Y factors via fin n for some n. Okay? We're almost done with the axioms, don't worry. There's something that we call axiom S, named after Scott because of Scott continuity, but really the slogan is we want to characterize the product topology. So we have an indexing type I, which is discrete. We have a codomain Y, which is discrete. We have a family of compact Hausdorff spaces indexed by I. And now we take the product of those spaces and then take some map to Y. And so the product topology is generated by boxes on finitely many coordinates. And so what we want to say is, well, okay, so you start with this thing is by the phi axiom, this thing is compact, Y is discrete. So by the previous axiom, we already know this is going to have a finite image. But what's not clear is, does that depend on only finitely many coordinates in the domain? And this axiom says it does. Okay.
But you know you need it? You know you need it?
We know we need that axiom. It's some of the least intuitive one, maybe.
But you can't prove it from the others.
We can't. Right. And then finally, we postulate that the natural numbers are discrete because we need some supply of infinite discrete sets. Okay? Good. I had till 12:10, right? So
Yes.
I should be halfway through my talk. Okay, so here's one theorem, which is that whenever you have a topos, it has an internal type theory. And so condensed sets are a topos. They are sheaves on the category of profinite set. Yeah?
You mean light? Do you mean light?
No, I don't necessarily mean light. I mean anything, but so fix, like you can do pyknotic. Basically, you can just choose a cutoff cardinal kappa and then work with that. It's,
Kappa condensed.
kappa condensed, right. Okay, and so the theorem is that all these axioms become statements in the internal type theory of condensed sets, which are provable, and the theorem is like, we have a proof.
You need to tell us the statement. What are the discrete ones and what are the...
Right, okay, so I'll tell you like how to interpret CHaus and ODisc. But yeah, I definitely don't want to go into this proof because it's like quite terrible. But it does provide a consistency check that somehow this collection of axioms doesn't allow you to prove false unless all of mathematics is used with. So that's good, but I don't really want to talk more about this, except maybe on the final slide. We're on the lookout for a computable model because the previous slide is very much extremely classical. But if we can find somehow a computable model, and I think Reid has some ideas there that I don't completely understand yet, then that would allow us to actually sort of realize this dream of getting a computer algebra system for general topology. Good. Let's move on. I promised you that I wanted to talk about directed univalence, and so let's do that. So far we've only talked about types, as in with our sort of topological space / set-like intuition, but we all know that propositions can be viewed as types. And so one universe that we get is the universe of open propositions. So we look at all propositions P that are ODisc, and we call that subtype OProp. And the curious thing about OProp is that it behaves like a directed interval. And so how does that work? Well, we make another definition. Whenever we have two ODisc types, X and Y, then we're going to define a type of directed paths from x to y. And what does that look like? So x and y are like points in the universe, and now we want to describe what directed points in the
Can you say what ODisc is in condensed sets?
Yeah, next slide. Okay, so what is a directed path? It's going to be a function from OPROP, this directed interval thingy, I claim, to the universe ODisc, such that false is mapped to x and true is mapped to y. So the endpoints go to x and y, and, well, don't think about, well, do or do not think about the stuff in the middle, but I claim like this is going to be a directed path. And like, why is it directed? Because false implies true, but true doesn't imply false, right? So there is some sort of arrow in OPROP. OPROP is a category. Very simple one maybe, but still. And then our theorem is that this collection of directed paths is actually naturally equivalent to the function type from x to y. So every function from x to y corresponds to one of these paths and vice versa in a completely natural way. Okay. So
is that your univalence? Is that what univalence looks like here?
That's sort of directed univalence. And we have a formal proof of this in Lean. So we start with like basic Lean, we write down all our axioms, and we just start messing around, and at some point we can establish this.
Is it canonical?
You get to judge. You get to judge. I think.
Tell us what the function is, or is that top secret?
No, I'll try to explain.
Okay.
I mean, it's I think it's canonical. I don't think you can find another natural equivalence, probably. So I think it's unique.
Oh, that's good. That's always good.
But it's also not completely straightforward. So, I think canonical sometimes means straightforward, but I don't know. Anyway, so...
Unique, but you don't know unique up to what.
Right, it's the unique one we found.
Unique up to the sum total of human knowledge.
Anyway, so there was this question, like, what does OPROP look like in condensed sets? And even if you think in the with just your topology mind on, like, what is, if a topological space is like a context, what is a proposition in that context? Well, it's a map from your topological space, that is the context, to prop, to the propositions. In other words, some elements get mapped to false and other elements get mapped to true. You view it as an indicator function, it's a subset. So propositions are like subsets, but in topology everything needs to be continuous. So you're looking at continuous functions to a two-point space with some topology. It's going to be the Sierpinski space. And propositions in this topological context will be open subsets. Or, like, at least, so that's what... well, no, open propositions, sorry. Open propositions will correspond to open subsets. So, and in topology, if you take a map from X to the Sierpinski space, that corresponds exactly with an open subset. Right, so the model for OPROP is Sierpinski space, and false corresponds to the closed point in Sierpinski space, and true corresponds to the generic point. And then false implies true is the generalization order. So you have one closed point, one open point, and the closed point generalizes to the open point. And then whenever you have a path f from x to y, that is something like a fibration over S, whose special fiber is x and whose generic fiber is y. And so I'll put a picture on the next slide to explain what I'm thinking of. So F is sort of this whole cylinder thing, and Sierpinski space is this two-point space, a closed point, open point, and F, you think of F as living over Sierpinski space. I mean, F was a map from O prop to the universe, it maps this point to the fiber above it, it maps this point to the fiber above it, and those are the only 2 points that you can see in the empty context. In another context, you might have a whole bunch of other points in other fibers. But anyway, so this point is a closed point, so this is the special fiber, this point is open, so that's the generic fiber. And this vibration is a local homeomorphism, exactly because we're mapping from, like the fibers are ODisc, right? We're mapping every point in O prop to something in the universe ODisc. And that meant that it's a local homeomorphism. And so, just intuitively thinking from topology, if you have a local homeomorphism, well, you take a point in the special fiber, well, then it extends to a little open neighborhood. But like you don't have that many choices for little open neighborhoods, so it's just going to extend to the generic fiber. So you get a map from X to Y. Every point in X extends to a point in Y. So having an F like this, a directed path, will give you a function from X to Y. Okay, and then why the converse is also true, like why you can, if you have a function, you can build something that looks like this, requires some work, but can also be done. So, proof ingredients. So one crucial ingredient is that we define the one-point compactification of the natural numbers and infinity. And so what is the definition? Well, it's all the functions from n to bool. So bool, you should distinguish from O prop. Bool is like discrete two-point space with the discrete topology. And we require these functions to be monotone. For the usual ordering on bool, false implies true. So false is less than true. Okay, and so why is that the one-point compactification? Well, you can take a function and so it can be send 0 to false, 1 to false, 2 to false, and at some point it sends a number to true maybe, and from then on it has to be monotone, it will keep on mapping numbers to true. So the point where it switches from mapping numbers to false to mapping numbers to true, that's sort of the natural number that is being represented. But maybe it never maps something to true. And so then it will be the point infinity. Oh? Okay. And then we have a finiteness predicate, which we call phi because finite, which just says, like, do you map something to true? If you map something to true, then you're finite because you represent some natural number. And if you map everything to false, then you're not finite, then you're infinity. Okay. And now we were looking at this picture over O prop. But this finiteness property, predicate, that's a map from n infinity to O prop. So we can pull back our entire setting to n infinity, and what is the benefit of that? Well, O prop is a really nasty type to work with somehow because it doesn't fit into our axiomatic setup. It's not CHaus, it's not ODisc, it's just like it's a universe of open propositions. But n infinity we can prove is CHaus. And why is that? Well, bool is finite, so it's both CHaus and ODisc. And so now we use the pi axiom to see that maps from n to bool, that's going to be CHaus. And now we take a subtype consisting of like all the x's from n to bool that satisfy this monotonicity predicate. And you unfold the monotonicity predicate, it's saying for all x and y, if x is less than y, then xi is less than x, I and j, sorry, I don't know. For all I and j, if I is less than j, then xi is less than xj. And you just structurally see that the axioms say this predicate is going to be a CHaus predicate. It's a closed predicate. And so n infinity is going to be a closed subset. And so hence it's CHaus. Okay. And so now we can use our axioms about it. We can apply them to n infinity. And the other point is that phi, we cannot prove that phi is surjective. but we can still show it's sufficiently dense in some sense. Whenever you have a subset of n infinity that contains infinity, it will contain an, whenever you have an open subset, like a map from n infinity to O prop, anything, if it contains infinity, it will contain an open neighborhood of infinity, meaning it will contain some natural number and all the natural numbers larger than it. That's the kind of stuff that we can prove internally, and we can use that and apply that, for example, to this phi and other predicates that we construct. And use that, and that allows us to make the preceding picture precise about taking points in the special fiber and mapping them to the generic fiber, and vice versa. Okay, so that was the proof sketch, and I was saying that like every sol can infer the axionomorphisms for functors that are only specified in objects, and now we want to like use that here. So we have this crazy correspondence between directed paths and function types. Every function from ODisc to ODisc extends uniquely to a functor. So let's prove this. We take a function from x to y, and now we're in computer mode, but we have to figure out how this f is going to be a functor and map this function to some other function. So by directed univalence, f corresponds to a directed path from O prop to ODisc, right? Which maps false to x and true to y. Now we post-compose with that map capital F, and we get a directed path between f of x and f of y. And now we apply directed univalence in the other direction, and it gives us a function f of x to f of y. And so everything is canonical, so this is compatible with identity maps and composition, which is a sort of like you have to do a sort of directed path induction proof to actually prove that, but it works. And here I really mean uniquely, like this extends uniquely to a functor. Okay, I told you a white lie, and Emily already asked about the white lie like minute one of the talk. I guess she saw this coming. Anyway, it extends uniquely to a functor if f preserves canonical isomorphism.
Kind of a theory.
No, I mean it's enough if it preserves isomorphisms. It doesn't have to preserve only canonical isomorphisms. And so the solution is either you work with univalence and homotopy type theory, and then you get this for free, or you just add this condition, like you say f has to be a morphism of groupoids instead of just a function. But you can't just work with homotopy type theory, at least for now, because we have no idea how to actually phrase our axioms in a way that makes sense for arbitrary higher dimensional homotopy types. So the sort of middle ground solution is we assume that all our axioms only apply to zero types, like h level 0. And we and all our theorems only apply to types in h level 0. And then it makes sense.
Times.
And then it makes sense in homotopy type theory. But yeah, we don't really know. Like here's one question: how do you do the image of compact and discrete is finite? What even is a finite type? Like that's not completely clear in homotopy type theory. So yeah. Anyway, so that's the little white lie. And so what the heck does this, like now we have this crazy theorem about every function is automatically functorial, and we claim that we have a model, so what does it mean in the model? And so that's what I want to end with. So we take the category ETK, so this is like etal over k, and really, so we just mean ordinary sheaves on a compact Hausdorff space K. For every K, we look at the ordinary category of sheaves, so we don't take like condensed slice over K, just ordinary sheaves on K. Okay, and then we take the groupoid core of this category for every K. And this gives you two stacks. So the groupoid core is going to be a stack of groupoids over the category CHaus, and ET is going to be a stack of categories over CHaus, and then our theorem says every functor of stacks between the groupoid cores extends uniquely to a functor of stacks, like period. Okay. Then, yeah, one little appendix about real numbers, because like you can do all this general blah blah, but in the end, like you claim to do some topology, so maybe you should look at real numbers. And we can define Cauchy reals and Dedekind reals, and we cannot prove that they're isomorphic with our axioms, but we can add one axiom, dependent choice, which is somehow really natural and it's true in the model, and I didn't present it to you yet previously, but it's completely innocuous to add this, and then they will be isomorphic. So I think this is a good reason to include that axiom. And so we can show that the interval is CHaus, which is good, right? It would be bad if it were not. And then there is a question that we haven't really answered yet, but which we're optimistic about. Like, every function is continuous, right? Because it's a map between condensed sets. But there's a different definition of continuity, which you can just write down as a first-order predicate with epsilons and deltas. And so, does every function from the reals to the reals satisfy that predicate? Is it metric continuous? And I'm optimistic, but yeah, we haven't really sat down to actually check this. Okay. Thanks for listening.